You mean you can't give a mass, or it has the wrong angle?
So all I mean is this purely asymmetric statement that there's no theory with just one massive spin 2 particle and lower spin particles, such that the spin 2 particle has a mass and the amplitudes of it grow more slowly than you have without these lower spin particles.
Is that because the amplitudes you construct don't give you the 6, or don't give you just because of this lower spin?
It's not obvious that that would be the only reason, because I can always have derivatives acting on those interactions. So, no, yeah, it's really some more complicated reason that you have to explicitly check.
I mean, the Graviton has a mass in the Randall Karch scenario.
Yes. So that's going to be more like the high dimensional scenario. So there comes along with the resonance of spin 2s, whereas the ours are shifting to just one massive spin 2 particle. So yeah, that brings me to the next point, is that we can soften massive spin 2 amplitudes in Kaluza-Klein theories, and these achieve this by having an infinite tower of massive spin 2 particles. So somehow all of these particles collaborate in just such a way that the cancellations between these diagrams. And that's going to be the subject of this talk. Now, one idea is to maybe try and find a finite truncation of the Kaluza-Klein theory, where you have only a finite number of massive nodes, and then this would provide a UV extension of theories of massive gravity like this. But there are arguments by Mike and Chris and Kelly Steele, for example, showing that generally you expect that this can't happen. So you need the whole infinite tower of particles. And there's some work, some interesting work by other people here, figuring out just how to write down the Kaluza-Klein inductions, keeping all these massive nodes. So capturing Melanie, Daniel Robbins used to be here. So this is the one solution to this problem. Another solution is provided by string theory, where here you have amplitudes that are exponentially soft in the UV, and this exponential softness is achieved now with having massive high spin particles with unbounded spin, which are exchanged in these amplitudes. But for this talk, I'm just going to focus on the Kaluza-Klein theories. So more concretely, these are the questions I'm going to try and answer in this talk. The first one is, how do massive spin 2 tree amplitudes get unitarized in Kaluza-Klein reductions of pure general relativity? And I should point out that very recently, this question was addressed in the case of 4 dimensions plus 1 compact dimension by Chibukula and collaborators. The difference here is that we're going to allow the internal space to be completely general. The second question is whether or not we can geometrically engineer the internal manifold in order to create parametrically large gaps in the spectrum of the Kaluza-Klein excitations. So if we could do this, what we could do is effectively find the UV extension of theories with a finite number of massive spin 2 particles just by pushing the heavier modes above the cutoff. And this would provide a sort of loophole to this no truncations argument that I mentioned before. And lastly, as a kind of bonus question, I'm going to ask whether or not we can learn anything interesting about geometry by doing this calculation. Okay, so let me now give an overview of the calculation before I dive into the details. So here's a basic overview. The first step is that we start with high-dimensional general relativity on some product spacetime, which is little d-dimensional Minkowski space across some compact internal manifold, which will denote calligraphic n. And then, in the usual procedure of Kaluza-Klein reduction, we integrate out the compact spatial dimensions, and we're left with some effective lower dimensional theory. And this lower dimensional theory, the imprint of the high compact dimensions that we've integrated out is that there are infinite towers of particles. And the masses and interactions of these particles are determined by the geometry and topology of the internal manifold. So concretely, the squared masses of these particles are going to be related to lambda, these lambdas, which are corresponding to eigenvalues of various Laplacian operators on the internal space. And And the cubic interactions, which I'll denote by G, are going to correspond to triple integrals of eigenfunctions of these Laplacian operators. Next, what we're going to do is calculate the 4-point amplitude at free level of massive excitations of the graviton. So we had the exchange of other spin 2 modes plus the graviton plus other particles that I'll show you later. And then we take this amplitude and we expand it at high energies. And what we find is that the leading order piece grows like the 10th power of the center of mass energy with some coefficient, which I'll call alpha sub 10. Then there's a subleading either the 8th piece, either the 6th piece, and so on. And these coefficients here are functions of the masses in cubic couplings. Now I'm going to invoke the fact that because this theory is really just high-dimensional GR, written in a complicated way, I expect that the amplitudes should grow no faster than the amplitudes in GR in any dimension, namely E squared. So somehow secretly all of these coefficients should really be equal to 0. So perturbative unitarity of GR is just the statement that alpha 10, alpha 8 down to alpha 4 are all going to be equal to 0. And these conditions I'm going to call sum rules because they give me constraints on the cubic couplings and masses in my dimensionally reduced theory. And as we'll see, we can directly derive these sum rules purely from geometric properties of eigenvalues and eigenfunctions. So this is going to verify that, in fact, amplitudes do grow no faster than E squared, as you'd expect from this physical intuition. But then we're going to try and extract some useful information from these sum rules. Hopefully they'll convince you that there's something interesting to be learned from them, even though they're sort of guaranteed to be true. Okay, so that's the basic overview. Maybe now's a good time for any questions if anyone's confused about what I'm going to do. Otherwise I can move on.
You 4-point?
Yeah, so this is all, I'm only going to do 4-point.
That's why you're 16 cubic?
Yeah, so this dot 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 also includes the quartic in this case. But more generally, there could be all the high points. But as I'll show you, all of these high point amplitudes can be rewritten into a lot of different ones using properties of eigenvalues and eigenfunctions. Okay, so let me move on to the bulk of the talk, which is about Kaluza-Klein theories. So the first half is going to be about the background space-time and the interactions of the different fields, and then I'll move on to amplitudes and sum rules. So let's start with this first one. So we're going to start with capital D-dimensional, the capital D-dimensional Einstein-Hilbert-Lagrangian. So my capital M sub capital D is going to be the high-dimensional Planck mass. Capital G is going to be the high-dimensional metric, and R is its Ricci scale. I then consider a background spacetime, which is a product of little d-dimensional Minkowski space, and calligraphic N, which is some closed capital N-dimensional manifold of volume V, which I'm also going to assume is connected and orientable. So then I can write the line element in the following way. This is mostly just an excuse to introduce some more notation. So my capital Latin indices at the beginning of the alphabet are the high-dimensional spacetime indices. Greek indices are the lower-dimensional spacetime indices. And middle lowercase Latin letters are going to be the internal spacetime indices. And then the internal coordinates are x, sorry, the low dimensional coordinates are x, and the internal coordinates are y. Okay. Now because of the equations of motion that this background must be consistent with, n is not allowed to be an arbitrary closed manifold, but to be consistent with the vacuum Einstein equation, it must be a Ricci-flat. So namely, the internal Ricci curvature must equal 0. So we need to look at the space of closed Ricci-flat manifolds. If we think about all possible Riemannian manifolds, then it turns out these closed Ricci-flat manifolds are relatively rare. The known examples are basically just flat tori, Malabi-Yau manifolds, which we know about thanks to Yau's 1978 group of Calabi's conjecture. And then there are the more recently discovered compact G2 and spin 7 manifolds, the first examples of which were constructed by Dominic Joyce. And note that all of these have special holonomy, which there are many experts on the subject in the room. One open problem is whether or not all compact Ricci-flat manifolds have to have special holonomy. As I understand, this is a difficult outstanding question in geometry. as far as we're concerned, all of the examples we know about have this property, and we're going to make use of that. Okay, so this was the background spacetime. Now we're going to perturb around it. So I take my full metric and I can write it as the background plus some leading order perturbation, which I'll denote capital H. So this is the high dimensional graviton. And then I can add nonlinear terms if I want to make my life a little bit easier. And then when I plug this in as a input action, I can easily expand everything out to find the quadratic, cubic, and quartic pieces, which is all I need for the 4-point amplitude that I'm going to calculate. And what I'm going to do in practice is make some special choice of these higher order terms such that I minimize the number of interactions which occur at cubic and quartic order. So if I choose things correctly, it turns out I can keep the cubic terms down to just 5 terms and the quartic terms down to just 5 terms when I throw away the transverse and trace with. So this makes the calculation much more practical. So that's just a convenience. So one last thing I should mention is that the leading order, the gauge transformations act on the graviton in the usual way, just as linearized diffs, some vector gauge parameter here. Okay. So now I need to make an aside, basically to introduce some more notation. And I'm going to introduce a bunch of bases of functions which correspond to eigenfunctions of certain Laplacian operators. So moreover, they're going to be real eigenbases, and they're going to be orthonormal. So the first one is the scalars, which are denoted psi sub a, and these are the non-constant eigenfunctions of the scalar Laplacian. So they satisfy the usual scalar Laplace eigenvalue equation, where the Laplacian, which is just minus box, gives me this positive constant lambda sub a acting on the function again. There's also the constant mode, which I'll include separately in all the equations I write. Similarly, I need some vector eigenfunctions of the spin 1 function around the Laplacian. So these have as internal spacetime index n, and this index I is going to label the various eigenfunctions. So these are going to be transverse eigenmodes of the vector topological Laplacian, which for the Ricci-flat case is again just minus box. And the eigenvalues I'm going to denote lambda sub I. And these are non-negative because the topological Laplacian is positively denoted. Okay, now thirdly, I need a basis of symmetric transverse traces eigentensors of the so-called Lignarowitz operator. So the Lignarowitz operator is just defined in the following way for Ricci-flat manifolds. And this is the natural generalization of the Laplacian to symmetric spin 2 tensors. So the eigenvalues are again denoted lambda sub this calligraphic I. So this calligraphic I indexes the eigenfunctions and eigenvalues of the Lignarowitz operator. A couple of facts that I should just review about eigenvalues and eigenfunctions is that these are all discrete and unbounded from above, and the eigenfunctions all form bases of their respective function spaces. So that's going to allow us to expand fields in an eigenvalue decomposition using these eigenfunctions. Okay, great. So now let's get to work. So we start with the high-dimensional graviton, and we break it up into its components. So it has an h mu nu component, which looks like a scalar from the point of view of the internal space. And there's this off-diagonal h mu n component, which looks like a vector. And then there's the HMN piece, which looks like a tensor from the point of view of the internal space. Starting with the scalar piece, I can decompose this using the eigenfunctions of the scalar Laplacian. So what I get is some coefficients, which are functions of the lower dimensional coordinates. And from the lower dimensional point of view, it looks like spin 2 fields. So these are the non-zero ones, and then there's the zero mode piece here. The normalized zero mode constant eigenfunction of the scalar Laplacian. And so once they're dimensionally reduced, these are going to correspond to my lower dimensional fields. Moving on to the spin 1 piece, now I have to use the Hodge spin 1 decomposition, which just means I can write a vector as the sum of a transverse piece plus a longitudinal mode. And then I can respectively expand those different pieces using eigenvalue decompositions. So the transverse vectors I can write as a sum over the transverse vector eigenfunctions of the spin 1 pushed around Laplacian with coefficients which are going to be vector functions of the lower dimensional points. And then the longitudinal piece I can again decompose using the eigenvalue decomposition into scalars. Lastly, I need the tensor decomposition. So in general, I can write a symmetric tensor as the sum of a transverse traceless piece plus the divergence of a vector. And then if I separate out the longitudinal mode of the vector and the trace of the tensor, I get a decomposition of the following form. And then I can again decompose each of these parts using the eigenvalue expansions appropriate for the basis of functions. So in particular, this first piece here, corresponding to the transverse traceless symmetric tensors, have some scalar-like functions from the point of view of lower dimensions, multiplying the different eigenvalues of the linear operator. So this looks a little bit messy, but fortunately I have that gauge freedom that I wrote down before, which I can use to fix a unitary light gauge to eliminate a bunch of these fields. This is the lower, the internal metric. Sorry, I'm not applying that. This is the trace part. So here I've shown the coordinate dependence of most of the fields, but later on I'm going to suppress them just to simplify things.
And some of the things you're canceling have to do with the lack of cohomology and Gravitron.
What do you mean?
For Ricci-flat compacts, you have no one cycles and so on. Are you using that here? Or?
No, this is actually valid for general Einstein manifolds, this decomposition. The difference would be, so here I've explicitly excluded informal scalars, which only exist for the spheres. So if any greater than 1, I won't have to worry about them. But I've included the killing vectors in here, for example. So if there's non-zero for speeding, I think there'll be something there. So unitary gauge means I can eliminate these 3 towers of fields. And if you want, you can think of this as a Higgs-like mechanism whereby, for example, these scalars are being eaten by these vectors to become massive, and these scalars and these vectors are being eaten by the tensors up here to become massive. As we'll see, these correspond to massive tensors in a low-dimensional theory, which I'll show you in a second. Which I'll show you right now, in fact. So if I plug this decomposition into my high-dimensional Einstein-Hilbert Lagrangian, I can use the orthonormality properties of the different eigenbases to integrate out the internal space. And I'm going to be left with some effective low-dimensional interaction, low-dimensional theory, which has these towers of particles. And after doing some demixing transformations to diagonalize the kinetic terms, I can simply read off the spectrum. And so what I'm left with is a massless graviton, which is denoted by H mu 0, which is the 0 mode from before. And I will draw that with a curly red line here. Then there's a tower of spin 2 particles, H mu nu, labeled by the eigenfunctions of the scalar Laplacian, and their squared masses, labeled by given by the eigenvalues of the scalar Laplacian. And these are positive because I've separated out the 0 mode explicitly. And I'll denote these by black curly lines. I also have a tower of vectors, A mu I, which are labeled by the eigenvectors of the spin 1 pushed around Laplacian on the internal space. And their squared masses are given by the eigenvalues of this Laplacian, which are non-negative. So there can be potential massless modes, which will correspond to vectors for which this index I labels the killing vector of the internal space. And I'll collectively label these by blue curly lines. I think my lasers just died, so I'm just going to use my hands for now. Oh, yes, I think so. Nice. Will this still works to change slides? All right. Lastly, I need to talk about the scalars. So there's a massless scalar, phi naught. This is the volume modulus. And then if the dimension of the internal space is greater than 1, there's a tower of scalars, again labeled by the eigenfunctions of the scalar Laplacian, whose squared masses are given by the eigenvalues of the scalar Laplacian. And I'll denote these collectively by a black solid line. And then there's another tower of scalars, labeled by the calligraphic I, which correspond to eigentensors of the Lignarowitz operator of the internal manifold, and their squared masses are labeled by the eigenvalues of the Lignarowitz operator. And this includes possible massless shape moduli if the admittance right directions in this multiplied space. And I'll denote these by the dashed olive line. Okay, so that's the spectrum. Let me make a comment about stability, actually. So everything here is stable up until this, possibly this last tower of scalars. And that's because the Hodge-Rundle Laplacian is positive definite. But the Lignerics operator isn't positive definite.
What was N?
Capital N is the dimension of the internal space. Yeah. So since the Lignerics operator is not positive definite, there can be finitely many negative Lignerics eigenvalues. And these correspond to tachyonic scalars in the lower dimensional theory, which therefore means the compactification is unstable. Fortunately, there's some known results about the possible possible negative modes of the Lignerics operator. Initially due to Mackenzie Wang, the mathematician, and then later by Gary Gibbons, Sean Hartnell, and Chris. So what these groups found was that if you have, for example, a positively curved Einstein manifold, which admits a killing spinor, which I've denoted by eta, satisfies this equation for some real constant kappa. Then it turns out there's a lower bound on the Lignerics eigenvalues, which takes the following form. So in particular, it turns out in the case of a Einstein manifold with zero curvature, the Lignerics spectrum is non-negative. And in this case, the killing spinor becomes a parallel spinor, which is the case when kappa equals 0. And this was also the subject of a paper by some mathematicians, Darwin Wang. So any closed Ricci-flat manifold which has a parallel spinor is going to be stable from the point of view of these compactifications. I mentioned earlier that all known closed Ricci-flat manifolds have special holonomy. They therefore admit parallel spinors. They therefore, by this theorem, have non-negative Ligneric spectrum. And so they're all going to be stable from the point by this criteria. And again, it's unknown whether or not there exists any examples of closed Ricci-flat manifolds which admit a negative Ligneric eigenvalue. This is just some open problem in geometry. Okay. But with this theorem under our belt, we're on slightly more solid footing as we move it here. So now we're going to look at the interactions. So far I've just been talking about the free fields. But to do the scattering amplitude calculation, I need the interactions of the different fields. So let's start with the cubic interactions. And to do the 4-point massive spin 2 amplitude, I need cubic interactions which have at least 2 massive spin 2 particles in them. So if we start with the self-interactions of the massive spin 2 modes, it turns out I can write them in the following form. So I've just shown you the first tensor structure, and there are some others, but it's not that enlightening to see them explicitly. The important thing to note is that they all have this cubic coupling, G, which is defined to be the triple integral of the product of scalar eigenfunctions of the scalar Laplacian. So like I mentioned at the very beginning, these types of integrals are controlling the strengths of the interactions in the low dimensional theory. So just to draw this in fine diagrams, I can write this interaction like this. And one interesting thing I can check is that if I vary this Lagrangian to find the Onshore interaction vertex, it takes the following form. So here, the epsilons denote the polarizations, and they factorize into this nice square structure, which is characteristic of the cubic interactions in general relativity. This is related to the GR equals Yang squared statement that you hear sometimes.
Sorry, what's the greater than equal to refer to?
The number of massive tensors in the cubic interactions that I'm going to derive, because I only want the 4-point amplitude with external massive tensors. If I wanted to do more general amplitudes, then I'd have to find all of them. But for this talk, I'm just going to restrict to this one. That makes life a little bit easier. Okay, so the interesting thing is that the massive tensors also interact with this Einstein-Hilbert-like cubic vertex, which you would basically expect because it's coming from high-dimensional GR. But it's nice to see it explicitly and to see that the strength of the interaction is controlled by this cubic coupling. Okay, moving on, we can think about also the cubic interactions between two massives, the two particles and the graviton. So here I've written these in terms of the lower dimensional Planck mass, which has the standard relation to the high dimensional one, where there's some factor of the volume which comes in. And I can again depict this in the following little diagram, where again the red squiggly line is my graviton. Again, looking at the Onshore vertex, I find it has this nice squared Einstein-Hilbert-like form. And in this case, this is basically fixed for you by the requirement that this is gauge invariant. So there's the usual Weinberg S-matrix equivalence principle argument, which tells you that every particle has to interact with the graviton with this universal cubic coupling with the Planck mass controlling the strength of the interaction.
Is there a simple way to understand where this square structure is coming from in this framework?
Well, aside from the Yang squared equals GR thing.
But suppose I know nothing about that. I just follow my nose, I do Kaluza-Klein, harmonic expansion. How does that emerge? Do you see a reason for this structure?
Well, if you imagine that you could start, say, with the high dimensional amplitudes and somehow directly dimensionally deconstruct them, dimensionally reduce them, then you would expect the cubic structures to be the same in that case. There's actually no way of doing that for a general curved internal manifold. You're supposed to be able to do it for toroidal manifolds, so there it would be clear where it's coming from. But other than saying it's just inherited from the high dimensional theory. Actually, there are some other nice causality type arguments which fix also this Einstein-Hilbert-like structure. I can talk more with you about them later, but yeah. So there is some sense in which this is inevitable for Okay. So that was the interactions with the graviton. We can similarly find the interactions with the vector, with the vectors. And the important thing to note is that the cubic coupling is now controlled by the following triple integral. So here I have a derivative acting on the scale eigenfunction, multiplied by another scale eigenfunction and the vector eigenfunction, which I define in the following way. So again, this takes the general form that I wrote down in the beginning. One interesting check that I can do in this case is to find the gauge variation of the Onshore vertex. And if I do this, I find it's proportional to the following combination of eigenvalues and cubic couplings. And it turns out I can write this as some integral where the integrand contains the following derivatives acting on the eigenvectors. And this combination cancels by Kiling's equation precisely when these are Killing fields, which verifies that everything's Onshore gauge invariant like it has to be. So it's a good check that everything's working like it should. And so lastly, I need the interactions with the scalars. So the first tower of scalars have cubic couplings which are again controlled by these triple integrals of three scalar eigenfunctions. And then similarly the second tower, the ones labeled by the eigenfunctions of the Wegnerius operator, have cubic couplings which are controlled by the following integral of derivatives hitting scalar functions contracted against the eigentensors of the Wegnerius operator. Okay, so this is all sort of straightforward, but actually sort of cranking the handle and curving everything out, not making any sign errors is a little bit tricky. But once you do that, you can go ahead and calculate some amplitudes. The last thing we need actually before we move on is the quartic interaction. And then again, this is controlled by a quartic coupling, which as you might guess is given by an integral of the product of four scalar eigenfunctions. And it has some tensor structure, which is not that important. Okay. So now we have all the ingredients we need to actually calculate some amplitudes. So let's go ahead and see what happens. So here's what the 4-point amplitude looks like schematically. I have a sum of the terms from the exchange of the massive spin 2 particles, the graviton, the vectors, the first tower of scalars, the second tower of scalars, and the contact term. And like I said before, we can expand this at high energies. And the leading piece grows like the 10th power of the center of mass energy, and then there are subleading pieces. And they all come along with some coefficients, which are denoted by alpha. And just to prove to you that I really did the calculation, here's what alpha 10 looks like.
Before you go on, in these diagrams, external lines are massive spin 2, right?
That's right, yeah.
But which massive spin 2? In the Kaluza-Klein tower, is it the first?
Any of them.
Any?
Yeah.
There could be different, they can have different masses.
Yeah, that's right.
Good, and the exchange part fields, are they, I can see their spin, but are they of any mass also, or?
Yeah, so whether their masses will be controlled by the non-vanishing cubic couplings.
Anything that's allowed, in other words, in the spectrum,
yeah,
will be exchanged. Okay.
Yes.
Okay.
Yeah. So this is completely general.
Okay.
4 points. This can be any of the KK dimensions. So that's why it's a little bit non-trivial to do this. All right. So just to prove to you that I actually did it with all the dimensional dependence and angles and stuff, here's the leading part of this alpha 10 coefficient. So you can see there's a dependence on this the scattering angle and the dimensions and the couplings, the Planck mass, and the cubic couplings and so on. All right. So I'm going to mostly spare you the explicit expressions like this and just tell you what the samples are.
Can you remind us what the lambdas were? Lambda A1, lambda A2?
Yeah, these are the eigenvalues of the sphere of the Laplacian.
Okay.
Right, I guess I should tell you, I'm labeling the external particles by A1, A2, A3, and A4.
Okay.
So that's why these are all appearing like this. Yeah. So these are the squared masses of the external particles.
You're looking for lambdas in denominators,
It comes from the exchange.
Inverting.
Because when I have the mass, I'm expanding everything at energy, so there's propagators, yeah. That's right, yeah. Good point. Okay. All right, so now I'm going to go ahead and tell you what happens when I enforce that alpha 10 equals 0. So what I find is the following sum rules. So these are conditions that have to be true of the quartic and cubic couplings in order for either the 10 particle amplitude to vanish, as we would expect from high-dimensional perturbative unitarity. So I find some simple-looking expressions, namely that the quartic coupling has to be written in terms of the cubic couplings in the following 3 different ways. Now, if you stare at this for a little bit, you might think about how we can directly prove such relations. The right thing to do is to consider the eigenvalue expansion of the product of 2 scalar fields, so psi A1, psi A2. Using the usual eigenvalue expansion, I can write this as the sum of some coefficients times the eigenfunctions. The coefficients are given by triple integrals, so these g's make an appearance again. And here I've introduced this Wick contraction notation, which just means that I take the 2 pairs of fields, which are indicated by the Wick contraction, and I expand them using the appropriate eigenvalue decomposition, possibly combined with the Hodge decomposition. So
Are these not just Clebsch-Gordon coefficients? The G's?
Sure, in the case of a sphere, these would be literally Clebsch-Gordon with some J functions going on. Yeah. But more generally, they're just these integrals of products of eigenfunctions, which in the case of the sphere would be spherical harmonics. Yes, that's a good example to have in the back of your mind. All right.
Well, they can be much more complicated.
Yeah, this is for general manifolds, so it can include arbitrarily complicated closed Ricci-flat manifolds, like complicated Claudiers.
But if you don't have a symmetry, isometry of the internal space, don't you lose control over Clebsch-Gordons and so on and so forth? Group theory is not that useful anymore, is it?
Yeah, so it's not a coset space, and no one knows how to explicitly analytically calculate these things.
So what are you assuming here? Nothing?
Nothing. This is completely general. This is all just following from the fact that I have a compact manifold. So Hodge theory makes sense. I can expand everything. The eigenfunctions form a basis.
And you claim that you have exact formula like this one, the second equation. Yeah, that one.
This one. Yeah, this is just. You can think of it as I'm just inserting a completeness relation between these 2 things, using the fact that the eigenfunctions form a basis of normalizable scalars on the compact manifold, and this follows. Yeah. So this is, yeah.
And what's the meaning of the second term, the V inverse term?
So this is because I've explicitly separated out the 0 mode. So these are the non-zero modes, and this is coming from the zero mode case. So it's just a constant because I've made everything orthonormal. There's like a 1 over root v in here. Okay. So once I know that I can do this, it now becomes straightforward to prove these sum rules. So remember that I defined this quartic integral, this quartic coupling is the integral over the product of the 4 different scalar eigenfunctions. So now I can use this eigenvalue expansion to evaluate this integrand in 3 different ways. Either in the S channel where I contract 1, 2, 3, 4, the T channel where I contract 1, 3, 2, 4, or the U channel where I contract 1, 4, 2, 3. And these are all just different ways of evaluating the same thing. And they give me these different looking expansions involving cubic couplings. So here this is slightly reminiscent of the bootstrap equations in CFT. So I've kind of used the wet contraction notation to invoke that a little bit. So these kind of associativity relations, I like the associativity relations which underlie the conformal bootstrap program. Yeah. Here it's just a sort of trivial property of the fact that eigenfunctions form bases. So everything is going to be just more complicated variants of this. But we'll deduce some non-trivial things. At least I have to get into that.
Should you have e to the power minus 2 or?
It's possible I made a mistake there, but oh yeah, you're just looking at this. Yeah, something's wrong. I think actually maybe there should be a square root. Yeah, there's some exponent that's wrong there. Thanks.
So what you really are using is that the product between the two functions is associative, right? So that's really what goes into it.
Yeah, if you want.
So I mean, you would say you have some arbitrary functions which have a product defined on them, and so I think, as far as I can see, this relation tells you that this is associative. So a little bit like the Jacobiator when you have a lead bracket, right? So which looks quite similar to what you're writing down and just tells you it's associative. So that's the only kind of constraint you're really putting on this theory.
Yeah, I mean, I've used the fact that the manifold is compact in order to be able to do everything. But in terms of, this integrand is just a product of, these are just functions, so you can evaluate them in whichever order. Okay, so this was the coefficient of the e to the 10 part of the amplitude. Let's now go to the subleading piece, the e to the 8 piece, whose coefficient I called alpha sub 8. And I'm going to set this to 0. Now in the special case where all of the external particles are identical. And from now on, I'm actually going to restrict to identical external particles, just to keep this talk within the hour. But if you want to know about the more general case, you can ask me afterwards. So from the e to the 8 part of the amplitude, we find the following sum rule. So here we have a term which is summing over the scalar eigenfunctions, where we have some coefficient times the square of the cubic couplings. And so you should think of this as coming from the exchange of the massive spin 2 particles. So here you have the expected square, and then there's this coefficient coming from the different masses. And then there's a term coming from the exchange of the graviton, which is manifestly positive. And the sum rule tells me that these things have to all add up to 0. Now, clearly the only way that this can happen is if one of these a's that occurs here is such that this cubic coupling is non-zero and this coefficient is negative, which means this lambda a has to be sufficiently big compared to lambda sub a1. So physically that means I have to exchange a massive tensor which is sufficiently heavy in order that it contributes a negative term to this summand here. So the precise requirement is that I have to exchange some particle with a non-zero cubic coupling such that its mass is greater than 2 over root 3 times the mass of the external particle. And in fact, this exact requirement was derived directly already by Mike Chris and Kelly Steele 30 years ago in the context of showing that there are no consistent massive truncations of Kaluza-Klein theories. And their proof is basically the proof that I'm going to show you later on. Again, it's going to follow from properties of eigenvalues and eigenfunctions.
Yes. So this equation looks like A1 has a special role as compared to the other indices. Do you have a similar equation for A2, A3, and so on and so forth?
Oh, so yes, I should have told you. Everything's identical, so I'm labeling all the particles by the same KK number as the first particle. So everything's A1
So
now.
it has to be done for all values of
but it has to be true for all A1s. So A1 is just any, I pick what amplitude I calculate, and once I pick that, this has to be true. Yeah, so in particular, that means every particle has to couple to a more massive particle. And if I repeat the argument for that more massive particle, I get an even more massive particle, and so on. And so I need the whole infinite tower of particles to have this unitarity requirement be satisfied. So in particular, that means if I make a finite truncation, this cancellation from the previous slide with either the 10 level will no longer happen, and that amplitude will grow like e to the 10 instead of e squared. So this is this goes well with the argument by Chris and Mike that you can't have massive finite truncations. A final note on this. Yeah.
That was the previous thing you already canceled, right? Now we're doing E8.
Yeah, but let's imagine that I stop somewhere, then the previous cancellations that happen will no longer happen. So it'll be violated already at e to the 10.
I'm just confused because I thought we had already that's what you were doing.
But that was assuming that I've kept everything. Because to derive that, I use the completeness, which assumes that I haven't chucked away the sufficiently high frequency ones. Yeah. Okay, so the final note is that these are actually exactly the same sum rules that you would get if you did this whole calculation, but instead of with gravity, you do it for Yang-Mills. So you start with high-dimensional Yang-Mills, Kaluza-Klein reduce it, and suppose that the amplitudes are now banded at high energy. I find two constraints from the e squared and from the e to the 4 and the e squared piece cancelling, and they're precisely these sum rules that I just found. And so what that means is that because Yang-Mills is valid on any closed manifold, these sum rules are also valid for any manifold. So I haven't made use of the Ricci-flat condition here. And you can also see that just by the fact that I don't use Ricci-flatness in the proof, which I'll show you in a couple of slides. Okay, now I'm going to do something which might seem like a bit of overkill, but hopefully it'll make things smoother later on. I'm going to rewrite the sum rule as some polynomial, which is a function of the ratio of eigenvalues times the square of the cubic coupling, plus some stuff which is positive, where in this case the polynomial is just some linear thing 4 minus 3x. And I'm going to plot that polynomial as a function of the ratio of these lambdas. In terms of masses, the square of the ratio of the exchange mass and external mass. So what the sum rule means is that I have to exchange a particle which is sufficiently massive such that this ratio lies along a point where this function becomes negative. So I need to couple to some particle which is, in this case, to the right of this in order for the sum rule to satisfy. This is just a trivial rewording of what I said before, but for the more complicated cases which we'll come to soon, it'll make life a bit easier. Okay, let me give you an example now. So let's go back to the original Kaluza-Klein idea and think of an internal space which is a circle. I'm going to label my eigenvalues by positive integers, so there'll be even and odd ones, where the eigenvalue is the square of this integer k, and then the eigenfunctions, the sines or cosines, appropriately normalized. So if I consider the scattering of identical particles, labeled by cosine wave functions in the internal space, then I can go ahead and calculate the triple integrals of sines and cosines, like I learned to do in high school, and find that the non-zero cubic couplings are the ones where the exchange particle KK number is twice that of the external one, or if it's 0. So in terms of the amplitude, this means I can exchange either a graviton or a massive tensor with twice the amount of external particles. And then I can explicitly substitute these all in and verify that sum rule is satisfied as it has to be. Okay. I think I'm going to skip the torus example, just so I can get to the interesting stuff. But basically, a torus is just a product of circles, and I can figure out all the cubic couplings and plug them in and check that they solve the sum rules. So let me tell you how to derive the e to the 8 sum rules. It's very simple, as you can see by the fact that there's only one line. So again, I'm just going to consider an integrand, which now has 2 derivatives, acting on a product of 4 scalar eigenfunctions. And I'm going to use some eigenvalue expansions to evaluate this in 2 different ways. So I can either contract these 2 fields and these 2 fields, or I can do the other combination, these 2 fields and these 2 fields. And when I do this and plug in the expansions, I recover the sum rule that I wrote down previously. Okay. Let's go to e to the 6 now. And I'm going to go straight to this depiction of it in terms of the graph. So I can write it in the following form. I have, again, some polynomial of the ratio of eigenfunctions, multiplying the square of the cubic coupling, plus some term here, which now corresponds to the exchange of the scalars labeled by the eigenfunctions of the linear operator. But the important thing is that this is manifestly positive. So again, I need to have some particle which is exchanged at a point where this function becomes negative. So in terms of the graph, that means I need to exchange a particle which is sufficiently heavy such that it falls to the right of the point of intersection of this red line with the x-axis. And now this point of intersection depends on n in such a way that in the limit that n goes to infinity, which is the dimension of the internal manifold, this goes to 4/3. So it recovers the previous bound. But for finite n, it's stronger. So now I'm making use of the Ricci-flat condition. So I'm getting some more information than I would have for a general closed manifold.
What's the origin of the term that's always strictly positive?
So that was so that this sum rule could be satisfied.
No, I understand.
Yes.
If you're getting something that's positive, you have to cancel it by adding something that's going to be negative. That's what you're using.
Yeah, so it's saying the sufficiently heavy exchange,
Yeah.
the exchange cancels, give an opposite sign contribution to the
Yeah, I'm just trying to
amplitude.
get the intuitive reason for why there was always that positive term, that was always strictly positive.
Oh, the always strictly positive one was for the graviton exchange. Yeah, that's what you have. So the graviton is, since this coupling is universal, it's always there. It turns out it's always giving you a positive piece. So you always need to cancel it with some negative stuff. So you always have to fall to the right of this line. So for example, for n equals 2, this is something like a half 1 plus root 17, which is 2.5, which is bigger than 1.3. Okay. And then there was an example with the torus again, but I'm going to skip that and go straight to deriving these. So I can do a similar thing where I have some integrand, but now it has 4 derivatives. So you can see at each step I'm increasing the number of derivatives that I have. This one's a bit more complicated because now I need to do an eigenvalue plus tensor decomposition of this combination of scalar eigenfunctions. But again, I can figure that out. I can evaluate this in 2 different ways. They have to be the same, so I recover the earlier sum rule. And then the interesting thing is that I can do this whole derivation in the case of not just Ricci-flat manifolds, but general Einstein manifolds. And this goes through, and you get some correction for non-zero curvature, which in the case of positively curved Einstein manifolds is strictly positive. So that means all of the consequences earlier also hold for positively curved Einstein manifolds. Although in that case, I can't strictly derive it from this S-matrix calculation. But I just geometrically, I can do this same type of argument. Okay, now let's go to the most interesting case, the e to the 4 amplitude, part of the amplitude. So this is the last one that I get to set to 0. And what I find is that I get some cubic polynomial of the ratio of eigenfunctions, multiplying the square of the cubic couplings, plus some term, which is only positive if the Lignero-X eigenvalues are non-negative. Or it's only non-negative if these are non-negative, I should say. So let's now assume that the Lignero-X eigenvalues are non-negative. Then in order to satisfy the sum rule, I can apply the same type of reasoning that I had before, namely that I have to exchange a sufficiently massive particle such that its value lies somewhere where this curve is negative. But now the interesting thing is that this curve, because it's a cubic, it turns around and it comes back up, in this case through the value 4. So that means I have to couple to a massive tensor whose mass lies in this range. And again, this point of intersection depends on n, and since the 4/3 as n goes to infinity. But the interesting part of this is this upper bound. So I have to couple to a particle which is different and not too heavy. So
But isn't it a disaster? Because you cannot pick and choose the mass of, I mean, you have all masses, right, being exchanged. So how can you...
this tells me I have to have at least one which lies in this interval. There can be, in principle, infinitely many.
Oh, at least one, sorry.
It's just the whole thing has to add up to 0, so I need at least some negative.
Yeah, okay.
You should also stay to the right of the red intersection.
I can only do them one at a time. Yeah, I have to be careful. Yeah.
Oh, I thought they were all being added superimposed. Like, the first one says to the right of 4/3. The second one says to the right of the red intersection. The third one says to the left of 4.
Right, but I guess in the case of the red line, I can satisfy this by being over here.
Yeah.
But then to satisfy the blue line, I now have to say I want
Yeah, but if you want to cancel all 3, then you need to be in that middle region.
No, I can't add them like that. because I could satisfy the red one and the blue one by having, say, one here and one here. There would be a solution, but there would be nothing in here. See what I mean? Yeah. But this is not so important. It's different, but yeah. I intend to satisfy these, but I can't just add them together like that. Okay, right, if I literally just add these polynomials together.
That would mean they have to deal with the same particle.
So if I literally just add these curves together, we'll find that this negative part will drag this down, so I'll get some worse upper bound. Yeah, that's what happens. Okay. So in equations, what this means is that if the Lagrange eigenvalues are non-negative, which remember was the case for all known closed Ricci-flat manifolds, then there exists some A star such that the cubic coupling is non-zero and lambda A star lies in this interval. That's just what I showed you in words before. So a nice corollary of this is that in particular, for closed Ricci-flat manifolds with special holonomy, the ratio of consecutive eigenvalues of the scalar Laplacian has to be bounded above by 4. This is a weaker requirement than this one. But if this is true, then this has to be true. Now, in general, closed manifolds cannot have such a bound. So here, the Ricci-flat condition is really important. And this is due to some results by Kaluza-Klein, which I can tell you more about if you're interested. And what this means in particular is that there's an upper bound on the gaps that I can have between Kaluza-Klein excitations of the graviton. So this answers that second question I had at the beginning. And because this is just a pure fact about geometry, it also applies to, say, smooth Calabi-Yau compactifications of string theory or G2 compactifications of M theory. Because there the spectrum of KK excitations is controlled by the scalar Laplacian again. So this tells you that there's a maximum gap on the bound between the excitations of the graviton also and then these compactifications. And I'm not an expert on G2 compactifications of M theory by any means, so I would refer to the work of many people here in this audience and at this institute for more on that. Okay. One interesting thing is to see whether or not this bound is optimal, so whether it's saturated, by any known examples. So it turns out it's saturated by a long tori. So in 2 dimensions, I can parameterize all tori by a single complex shape moduli, and all the conformal and equivalent ones lie in this fundamental domain, the complex plane, and all of the shaded ones satisfy the Scalars bound. More generally, if I consider a tori an n-dimensional torus, which is the quotient of Euclidean space by a rectangular lattice, which is generated by integer combinations of these unit vectors, where one of them is taken to have length greater than or equal to 2 times the other ones. So that means that it's stretching one of the directions, so it looks roughly like a circle. And it also saturates the bound. So the bound is optimal in every dimension. Lastly, we want to try and do a more realistic or more complicated internal space, like a Calabi-Yau manifold. Unfortunately, there's no known analytic expression for the Ricci-flat Kähler metric on a general Calabi-Yau manifold, or even any non-trivial examples, but they can be determined numerically using Donaldson's algorithm to approximate the metric, and then you can figure out the eigenvalues and eigenfunctions. And this was done explicitly by this group by Volker Brown, Tomas Gravitzi, Michael Douglas, and Bert Overik. And I'm just going to shamelessly steal their results and tell you what they got. So, for example, for the Fermat quintet, which is the hypersurface and complex projective force space defined by this degree 5 homogeneous polynomial, the lowest eigenvalues of scalar Laplacian with unit volume normalization are given by the following values. And if you think about it, you take the ratios, you can see that they're easily within this factor of 4. And this is also true for all of the other examples that they considered. So this is another check that's by no means exhaustive. Okay, and lastly, we can prove this. So now we have a 6th derivative integrand. There's an appearance of the Lagrange Laplacian. And again, I'm just going to evaluate it in 2 different ways. I expand everything out, and I recover the sum rule that I wrote down earlier. Again, this generalizes to Einstein manifolds with non-zero curvature. And for positive curvature manifolds, the correction is manifestly positive. So I can get a bound on the ratio of eigenvalues for positive curvature Einstein manifolds that admit a filling spinner. Examples of such manifolds are Einstein Sasaki manifolds with dimension less than or equal to 9 by the earlier bound by Wang at least Hartman on code. Yes?
I'm just curious because when you talk about these R greater than 0 situations, I mean, That doesn't tally with your original starting point of
Yeah.
Minkowski times
That's right.
thing.
There's no scattering interpretation of these.
Right, okay, so these are just statements in their own right about these manifolds.
Yeah.
Yeah.
Presumably one could hope to do like a Freund-Rubin type magnification, and there should be some, if I have an ADS bulk, I can do some dual CFT calculation, which would give me some
Right.
downs
But
like
the whole
this.
analysis will be much more complicated.
Yeah.
You've got these form fields to
Exactly. But I can just go in and do this simple.
Yeah.
Okay, so let me conclude. So we've seen how geometry achieves the unitarization of massive spin to amplitudes by satisfying these particular subrules that I've written down. And one consequence of these is that the Kaluza-Klein excitations of the graviton, their masses cannot differ by more than a factor of 2 for the excitations which are adjacent. And so this means I can't have arbitrarily large gaps in the spectrum. So that answers my first 2 questions. And then we saw that this could be interpreted as some interesting statement about eigenvalues on Ricci-flat manifolds with parallel spinners.
Why is it 2? They 4.
For the masses it's 2, for the eigenvalues it's 4. Look at this squared. Right. So I started with some questions, so I'm going to end with some questions, and these are going to be in exponentially increasing order of difficulty. So the first one is, are there any further constraints that I can derive in the spectrum by considering higher point amplitudes? The second one is whether or not geometry is the only way to unitarize massive spin 2 amplitudes without using high spin particles. And then the last one, which I have no idea how to solve, is whether or not the string theory solution to this unitarization problem is the unique one with high spin particles. This is obviously a difficult outstanding problem, basically to prove what theories of quantum gravity we can. I have some thoughts on these first 2, if you want to ask me about them, but otherwise I'll finish it up there. Thank you.
You can finish on time, yes.
Just a comment or a question. In the standard model, all particles have